then if you go to very, very high altitude, to astrophysics, and they don't have much data to work with, so their numerics are superb, especially on MHD, because they rely so much on modeling techniques. So geospace is kind of in the middle. So we have some data to work with, but we don't have that much effort putting in numerical modeling. So there's a reason that's probably a curve that people see. Where are we on the modeling effort at geospace? But I think my own opinion is LFM is actually somewhere here. But we need to make the community know that we have this piece of art and we can do better than what we're doing now. So that's also a reason we want to do GAMERA. So how are we going to do it? So we're going to throw away everything that LFM's already, every piece of source code that LFM's already got. So we start from scratch with more than Fortran. So we don't want library dependence. So the only library dependent for the code is going to be standard ones like NCAR and HDF5. So you can just get the code and run on your laptop system. And also we would preserve most numerics underlying the LFM code, because we've already done so much work to show how good the numerical method is, the quality of the numerical methods. So we don't want to do starting from something completely different. And there's another reason why we do this is when I first started this, I tried all kinds of numerical methods. And then, when I started with this with the graduate students, like, I'm a graduate student, I have nothing to lose, so I'm just going to try whatever I think is best to try. Then I did all kinds of methods, and eventually I went back to the LFM type of scheme because I couldn't beat it. So it's still the best. So we went back to the LFM scheme. Based on that scheme, we implemented some necessary upgrades to the numerical methods to make it even look better on test problems. And also the ultimate goal is to develop a general application, flexible, portable, exascale-ready MHD code with a nice coupling software to do a model coupling. For example, we're looking forward to do coupling with WebCommX plus gap region physics. So we have simulation from the surface of the sun all the way to the ground. So I'm not sure what we're going to do with it, but that's something we should think about when we start to do this. Okay, based on these criteria and based on the these requirements, we get down to GAMERA, and here is GAMERA. And this is GAMERA, the name. Different people might have different, this is actually the acronym that all the team agreed now. And it's Grid Agnostic MHD for Extended Research Applications. And if you Google GAMERA, it's actually a giant beast from Japanese comic books. And this is the original GAMERA from John's email. So the first time we heard this name is John said, John kind of mentioned that he did not like the name LFM very much, so he wanted a new name. So he named it GAMERA and sent us an email with this picture in it. And everybody's kind of, wow, that's something. And that's John's interpretation of GAMERA. And this is Kareem's. Kareem is actually the master coder behind the GAMERA. So he's a mathematician. He's going to come here to give a colloquium in September, hopefully. And he has a different interpretation of GAMERA. And apparently you can see that you need more physics to do this than that one, right? So it is John's GAMERA. So there's so many features in GAMERA, including, we do ideal resistive Hall MHD. And we also have multi-fluid branch, does track, each species with their own force balance. And we have a semi-conservative and fully conservative solvers to conserve either plasma energy or total energy. And it's based on finite volume from 1-dimensional to 3-dimensional. And it's you can do either on Cartesian or very distorted curvilinear grids. And have a very high order advection scheme, as you see from the first PIL paper. And also constrained transport, flexible flux functions for example, for some problems you wanted it be more robust on rarefaction waves, you can change it to some other flux functions than the default one. And also we do semi-relativistic corrections, which is also known as the Boris correction. And Korean and I were talking about putting the GR MHD, which is the general relativistic MHD, but it doesn't seem like we need it for geospace. So we're going to put that side first. And then we do very accurate high-order background field treatment. So if we put in a dipole in our grid, it's exactly equilibrium, so you don't generate weird stuff. And also the ring average for the axis singularity. In cylindrical geometry, you always have a singularity along the axis. So we did some serious upgrades on that one. And these are the numerical implementations that Kareem is probably the best person to introduce. And the ultimate goal is we want the software developed, and that's a piece of code. The knowledge should be owned by the whole community. So we want to open source and people to use it. So that's the point we're doing this. So I'm not going to go through all the details here because every piece is so complicated. So I'm just going to go through some, the green ones, which is advection scheme. So what we did to improve the advection scheme in LFM, and what we did to do a nice treatment for the spherical singularity. So these are the upgrades that I'm going to talk about. So basically two. One is we went down from 8th order centered reconstruction to a 7th order upwind reconstruction. And we also put in a non-clipping limiter, which does some very nice things for simulations like a current sheet, like Harris equilibrium. And also we did a very high order, which is piecewise parabolic method for the conservative treatment of the axis singularity. So we can get around with the problem that the cells are clustering near the pole, and then your time step is restricted, and to get away some of lots of numerical instabilities. Yes?
And so what drove you to do the first upgrade there? So it was 8th order center, and so decided to go 7th order upwind. Why?
There is a reason. That's the next slide. Okay, so why we're going to do upwind here instead of centered reconstruction. So the MHD equation or fluid equation is basically in a conservative form, which is a divergence equal to a time derivative. And that's a source term. And the source term treatment is very problem dependent. So there's no uniform way to do that. It depends on the problem itself. So we're not going to look at that term first. So we just look at the advection term, which is in the linear case, it's just the advection term. So which means you advect. This equation tells you advect something in the direction of in the velocity of u from, let's say, left to right. So the original LFM scheme uses a high order derivative or approximation to the derivative, which is this form. So left-hand side equals to u times the 8th order numerical derivative. That's the 8th order is the default. And then plus, the 9th order, whatever left. And there's other 10, 11 things. And these are truncation terms. So if we just solve this equation, regardless, just know that. And this is the actual equation solved by the numerical method. So this is the equation, the theoretical equation. And this is the actual equation solved by the numerical method because we are taking away of these truncation terms. And you can see that if we do this, and this is the equation plus a couple of terms. The first one, leading term, is a 9th order derivative, which is a dispersion. So we know that, first order, third order, fifth order, these derivatives tells you a dispersion. And 10th order, even order terms, these are diffusion, which means that you're solving an equation with a dispersion term there to try to deform your solution and make it doesn't. You can argue that this alpha 9 could be very small, but sometimes it's not small enough to see, to totally ignore this effect. So with the 8th order solution, and then you have a 9th order dispersion, and the 10th order diffusion is usually not enough to damp out the 9th order diffusion. So sometimes you see, in very extreme flow conditions, you see oscillations for very high order schemes. So that exists in the high order scheme. But if we look at a 7th order upwind reconstruction, so which means that we're using the 7th order numerical derivative to approximate the d rho dx. What you left is the 8th order diffusion and a 9th order dispersion. So this is much nicer than the other one we saw because the 8th order diffusion acts on the whole solution together with that term, so it damps out the diffusion. So you have an 8th order diffusion, damps out the 9th order dispersion. So the solution is more smoother and less dispersive in this case. And actually, experiments we found that if we use the 7th order, we got a much more symmetric solution. Sometimes it should be lots of flow conditions. It should be symmetric. And then if we do this, it's much more symmetric, and it's better behaved flow conditions with that. Yes?
Okay, so so you got rid of dispersion at the expense of introducing more diffusion.
Yeah.
So,
Yes, I understand.
Why is diffusion better than dispersion?
Well, it's not. So dispersion can give you grid scale noise. Right, so you disperse your solution. If it's it's a Gaussian, then whatever, and a square wave, and you have the Gibbs from it, it gives you some like grid scale noise, and those grid scale noise in instabilities can grow really large. So if, for example, you see like in Kelvin-Helmholtz or radiator simulations, sometimes it should be exactly symmetric, but they're just not. And then letting the leading term to be 8th order diffusion kills those grid scale noise, which does a much better job on those, these numerical instabilities will be killed. Whether it's enough or not, that's a different question. So we do have a price to pay. We do know your solution for square waves is probably a little bit more diffusive, but you kill other numerical noises, which is a trade-off. And then the price is not that expensive, and I'll show you later. Okay, so this is why we went from the even center to upwind reconstruction. So there's another step we did, is we put in a non-clipping type of limiter. So this is a traditional reconstruction method showing how the derivatives are calculated. So these are the cell I and cell I plus 1. This is cell interface, I plus a half. And to find what the value across the interface, and we usually do a high order, 8th order, or 7th order interpolation to get a value here. And then if we use a limiter, which is a TVD limiter, and here we use the partial donor cell limiter, which is a PDM limiter, and the limiter will tell you, it's bad because it's higher than any of the others, so I'm going to clip it. So if you use a limiter, and this is always the value you get. So it's a small error, but sometimes it's going to give you very bad results if you want to balance the thermal pressure and magnetic pressure exactly at that interface. So we put in a smoothness detector based on this kind of conditions, depending on the derivative of the shape we're looking at. And if the smoothness detector says, okay, it's smooth, and then we relax the limiting, and then we use this value as the interface value. Otherwise, we always keep that value as the limited value. So the limiter is keep the solution TVD, total variation diminishing, for linear cases, because nonlinear cases we don't know, and nobody has to show that if the solution is supposed to be that. So this is another upgrade. So put all these things together, and we did a very nice test case, one-dimensional solving this equation using the schemes I just talked about to advect 4 shapes: Gaussian, square, triangle, and half circle across, in this direction. So it's an advection equation going this direction, periodic boundary conditions. I'm going to let it propagate to one period and see how good the scheme behaves. So here is the animation. Let it go. So you can see they're going this direction. And the square wave, you have 2-3 cells to resolve the contact discontinuity. Gaussian peak does not get clipped. And these are a little bit deformed on these because these two are pretty extreme. So, but if you look at, if you go back, the red one is the initial profile, which is a theoretical profile. The circles are the advection results after one period. And you can see that the Gaussian peak is preserved very well after a couple of cells here. And then the square, we did get like 2 cells in the middle, maybe another cell, 3 cells. So this is actually the price to pay. So if you use an 8th order scheme, and the resolution for the square wave is even better than this. So I would say the width for here is 2 or 3 or 2.5, and the 8th order is 2. So that's the trade-off we made here. But you look at the Gaussian, and then these are less. These two are pretty extreme because usually these two would not happen in the real system because you have a first order discontinuity and very extreme changing, very rapid changing in the slope here with only like 12 cells here. So compared with the clipped version of the limiter, which does not have the smoothness detector, and this is the result. You can see that it does a pretty good job. It doesn't affect the square wave, but it does chop the top here. So you have a flat region because of the TVD limiters does not like peaks. Every time it sees a peak, it wants it flat. So there you go, and you have a little bit here, and which is better in these ones. So these are the basics of the effects of the new scheme. And I've done some tests with other methods, and you can see that these are 4 types of different methods. They're very different. So the first one is the traditional standard TVD limiter, which is called mean mod. And you can see that it is very diffusive. So it has the diffusion, numerical diffusion is so large, it tried to move everything to be an error function. So that's the second order scheme. So the third order scheme is a standard PPM, which is a piecewise parabolic method. And you can see that the PPM does a very good job on the contact discontinuity, but it chops the top of it, trying to make everything to be a square. That's what the PPM does. And we know is actually very nice on the Gaussian, triangle, and half moon. Everything's smooth and nice, but it does not do very well on the contact discontinuity. So, and finally go back to the 7th order, upwind with non-clipping. And you can see that this is better than in any of the 3. And you could argue that I used exactly the same time stepping method for everything for test and same delta t. And you could argue that for these 2 methods, you can combine with a particular type of time stepping, say Runge or even higher order predictor corrector type of things. But the thing is that if I do the same thing for that, and this will look even better. So it is fair to say that we do see some good features in the high order scheme here. So come back to why we want this is because we want to do currency simulations like this. So this is 1D MHD equilibrium called Harry's sheet problem. So theoretically, it's just so if you solve the MHD momentum equation with time stationary solution, so ddt is 0, and the flow is not moving. So you got a balance, actually balance between grad p and j cross p. So that's what the equilibrium does. And if you solve this equation in a slab geometry with plane fields, that term is 0. So you solve the equation and you find the theoretical solution with that. So B, pressure, magnetic field, pressure, and density follows this. So if you put these initial conditions in your MHD solver and run it for a very long time, you should get equilibrium, or your solution should not change. So that's actually one measure of how good the scheme is. So the reason we did this is because the 7th order scheme with non-clipping feature does keep the equilibrium very, very well for a very long time. What I'm showing here, only t equals to 20, and you can run all the way to 100, does not change the form. And then if you compute the total energy change, which is this line, which is the magnetic energy plus thermal energy, it's always a straight line, and the change is less than 0.05%, which is very good on 64 cells. So I only have 64 cells. And this is the reason why we want this upgrade, is because we did the same test with the original scheme. This is what we get. So you can see that on 64 cells, and because this is the plasma pressure, because of the clipping, it's always flat here. So after one step, the plasma pressure shows a mismatch between the plasma pressure and magnetic pressure. So some waves is a tiny bit wave is generated in the middle of the current sheet. So it propagates out, interacting with the boundary condition that I got this like standing wave-like structure. So You could use more cells to do that, to delay these generation of the waves, but because of that clipping, so the numerical equilibrium is always off from the theoretical equilibrium. But with the new scheme, it's always on that curve, which is very nice. So this is a very, very big improvement that we did in the schemes, and we're looking forward to use this, in other complicated problems. Okay, so I'm going to move to a slightly different topic that we do the ring average, which we treat how we do the spherical singularity, because LFM can run on Cartesian grids, cylindrical grids, and spherical grids. So spherical grids, and this is a polar view of a spherical grid. Let's say it's a cylindrical geometry. It's two-dimensional. So you're looking down from the North Pole, well, you can see that when you're coming from the low latitude to high latitude to the pole, the cells clustering pretty bad. And you can see that if you compute to the area or the size of the cells, so if it's a grid by n by n grid here, longitude, latitude, and the ratio between this cell, the volume or phase ratio between this cell and the innermost one actually goes 2n minus 1. So if you have 100 cells, which means your cell here is 200 times smaller than that one, which restricts your delta t pretty bad. So you have to use a very, very small dt if you go with this grid. And if you do some math, and you can show that the dt actually go with 1 over n squared, which means that you double the resolution for an MHD solver, your delta t becomes 1/4 of the previous resolution, and which is pretty bad. So to get away from this, we used to implement the ring average technique, which look at the grid, effective grid looks like this. So this is actually effective grid. So we treat the solution in some way that the effective grid actually looks like this. So you have, you have 8 cells. This is an example. You have 8 cells in the innermost region, and then 16 outer there, and 32 and 32, and the next one is 64. So the azimuthal number here is 64. So by this, and if you do this, and you can see that the cell size ratio goes down to 2n minus 1 plus 2n ring minus 1. So n ring is the index of the outermost ring that we do this ring average. For example, for this one, it's go down from 200 to 10, which is not too bad. Okay, so how are we going to do this? So this is just an idea. So we have an effective grid like this, but doesn't mean that the actual computational grid has to be that. So you could do something like this. So you generate a grid which is different. So when going down to high latitude, the grid number of cells decreases, but that's going to make your code really, really ugly, and you don't want to do that. And it's not very easy to move on to higher resolution. So the ring average is actually a post-process type of code. So you do the regular finite volume and finite difference solve. And after you solved everything, you put in this technique to make the effective solution look like what we have there. And then now your dt is now determined by whatever here. So I'm going to start with the example so you see the polar region here. So this is the region that the clustering of the cells give you really bad dt. So what we do is that we use the ring average to make the solution behave on this grid. So you can see that you have less and less cells as you're approaching the pole. And usually, experiment told us that usually, the innermost cell should not be less than 8. If it's less than 8, it doesn't do very well. So we usually use 8 here. So the azimuthal cell here is 64. And if we take one ring as an example, which is the second one, and you can see that this is the blue one that I'm taking, and I plot as a number as azimuthal. So this is the initial data for each cell. And you can see that these oscillations, wave numbers, high wave number in each cell, these are the ones give you a problem in the delta t. So we take that, and then we divide them to 16 averaging regions and do an average, and that's what I get. So I get the initial data. I average them by part, every 4 cells. So I get, these crosses are average numbers. So after that, you're actually done. You're actually effectively reducing your cell size to be this, because you're not allowing any variations within each chunk. So I'm calling each blue one is a chunk. And so if you put these values back to the actual cell, you could work, which gives you a piecewise constant reconstruction. So each cell has a constant value. Each chunk has a constant value. So that works for fluid simulations. And it's easy. It's really simple. So you just need one step and averaging and put it back. But the problem is that you're actually introducing a artificial jump across each chunk, which put in numerical diffusion in your finite volume solver. So it could work for fluid, and it just in the polar region it's more diffusive. So we don't want that. And since we have all the average values, and we went to the fourth order method, which is a piecewise parabolic. So what we have is that if you take an example, I have all the averaged values. I can use a high order method to find out what the interface value is supposed to be. Use the piecewise parabolic PPM method, and to make sure that it's monotonic within each chunk. And there's another constraint that the redistributed cell volume or the mass should be exactly the same as the one before reconstruction. So if we do this PPM reconstruction, so the redistributed value would be exactly the same as the averaged one. So I don't lose any mass, momentum, and energy in this process. So if I do this, and this is the reconstructed value I get. So compared to that one. So it follows the solution mostly, and it knocks out all those variations. And if it's a finite volume method, which uses conservative updates, and this is exactly the same as you do the grid. You manually do the grid. So this process is actually used in the fluid simulation, and this is actually done. So you just do the solver with the longitude, latitude grid. After that, you put in this kind of treatment, like a filter, and then you're done with it. So this is a pretty simple piece of code. It's not that complicated. So let's take a look at some test simulations. So this is a pretty extreme simulation. So I'm simulating a blast wave in a cylindrical geometry. It's a 2D problem. Uniform density, uniform pressure, zero velocity. I put a high pressure region here, which is 100 times higher than the ambient fluid. So the wave is going to gonna blast and go through the pole, and we can see how good the ring average does on that problem. So you see that's a shock. So this is the global general picture, and this is zoom in. So that black box is that one, and this is the effective grid we use for the simulation. And you can see that you don't see deformation of that. If you plot the contour, it's a circle, very nice circle. And this is a little bit difficult to quantify this because we start from something asymmetric, and then as you propagate here, the resolution become finer and become But overall, you see the shock move through this region nicely and without deformed and without losing in mass and kind of things. So, and this is the same as the blast wave. So one thing about this ring average technique is that if you don't keep the mass, momentum, and especially energy conserved across the pole, and you're actually changing the shock speed and shock condition. So if I put in an FFT filter here, I would see my shock would go something like this. So that's nice. And if we want to go more quantitatively, and this is a couple of snapshots I'm showing the effects. So this is the same simulation. The yellow circle indicates where the averaging is started. And you can see that 3 time steps. And I'm plotting the total mass, total momentum, and total energy as a function of the simulation time. And you can see that mass is conserved. It's finite volume. It has to be conserved. If it's not, something's wrong. And its total momentum is always 0. And if you zoom in, the error is 10 to the minus 14, which is rounded off. And then the total energy is also conserved. So this is hydrodynamics. I haven't put in any magnetic fields yet. So you can see that the method conserves momentum, mass, and energy very well in the average case. And this is an interesting plot showing the variation of the delta t, which is time step as a function of number of cells. So I'm doing n by n grids. So the this curve showing you the delta t as a function of m if I do ring average. The other one with the slope of -1, which means that I double the grid, my dt becomes a half. And the other one shows you that I do the same simulation without ring average. So it shows you that if I double the grid, my dt becomes 1/4, which gives you a slope of -2. So at 1,000 by 1,000, and then the difference, the improvement in the dt could be like 100, factor of 100 easily, or even 200, more than that. So that's why we want this technique in the 3-dimensional simulations for a spherical geometry. All right, so if you're working with fluid simulations and you're done, and the ring average is done, and with the high order advection and the ring average, you're okay. But with MHD, things gets more complicated, which is sometimes can be disastrous. So if your MHD model uses everything at cell center, some people do that. You define the magnetic field at cell center, fluid at cell center, and then you're done. So you basically do the same thing for every component. And after the reconstruction, you do a divergence clean step to clean your divergence of B. So that's possible, but we know that usually we don't want to do divergence clean for simulations because sometimes you got numerical results coming out of nowhere. You have no idea what's going on. So we do this kind of E-grid, which is called constrained transport. What we do is that lots of simulation, MHD simulations, because they have to deal with the B field. So we define the fluid variables at cell centers, and we also defined the magnetic fields or magnetic flux at the interface, and the electric fields are on the edges. So by doing this, the code, as long as the initial divergence is 0, the code preserves the numerical divergence to round off. And because of the constraint of divergence free, so doing ring average for magnetic flux is more complicated than the fluid. And unfortunately, in lots of MHD simulations, if you do a spherical MHD without any treatment for the polar axis, it's unstable, unfortunately. So we have to do something to do that. And this is an algorithm, and it's fairly complicated, but the idea is actually pretty interesting. So looking at that, this is my axis. I'm looking at a cylindrical geometry. So this is the azimuthal direction. And I have 2 magnetic fluxes or magnetic components to vary. One is the J flux, one is the I flux. So K is the direction that's around the pole. So I can do, what I'm showing here is a chunk. It's an averaging chunk. So these small ones are the actual computational cells. So you can do the same thing to redistribute the flux. Let's take a look at the J component. So we can redistribute J to there, and we can also redistribute phi I along here. And then what you're going to do with the phi K. So you cannot just redistribute the phi K component, because you do that, you're not going to guarantee you got the local divergence free for each small cells, because the reconstruction does not guarantee the divergence is 0 for each small actual computational cells. So what we do is that if you look at Faraday's law, whenever I change the flux in this phase, Faraday's law tells me that you can you d phi j dt is an electric field. So what we do is that we reconstruct this phase, and we put the changes in the electric field here, and then we do all the way across, and then we do we reconstruct the flux in this direction, and we put the changes as an electric field along these edges, and we leave the K electric field don't touched, because that's shared by the 2 phases. So once you've done all these reconstruction and you compute all the delta EI and delta EJs, and you use the changes in the electric field, put in the Faraday's law to compute what the phi K should be. So by doing that, and you can conserve the divergence exactly after the reconstruction step. So that's actually the additional step for magnetic fields we should do. Okay, so here is a advection problem. So we look at a advection problem, which is advecting a field loop across this direction. This is actually it's a standard MHD test problem, very violent. It's a pretty hard test simulation to do. So the idea is to put that simulation in a cylindrical geometry to see how the ring F behave. And this is what we get. So I'm gonna So what we have is we have a bunch of field loops rounding here. So B field is 0 elsewhere. It's circulating here, and that it's propagating in this direction. It's a very small B field, so it's a super alphinic in this direction, and let it go through pole, and let's see how the magnetic energy goes. So it's advecting in this direction, and it goes through the pole, and you don't, these are actually grid effects. It might have a little bit artifacts, and mostly, it goes through the pole very nicely. It does lose some energy because of the radiating of these powers. And if you look at the changes in the magnetic energy, so from time 0 to 1, and we actually go down about 5%. So in the Cartesian case, if you go to 2, time equals to 2, we go down about 5% changes in the magnetic energy. But that's not a very exact comparison because my grid resolution is non-uniform, and it's a completely different type of simulation. But you do see the ring average technique handles the topology of the field very well. Although there's some a little bit artifacts, but it does not grow with time. It does not hang around at the pole. So I think this is a pretty good example. All right, so this is a pretty picture. We come back to the blast wave simulation. So at the same blast wave, we put in a very strong magnetic field here and see the shocks going through the pole without deformed. So this is the plasma pressure. This is the magnetic pressure. This is the plasma pressure. And you can see, this is the plasma confined here because my field is here. And you see that then, a couple of shocks going through this region without be deformed, and that's the reason we want to do this. So it's pretty nice, and these are 2D, and I have one plot for 3D, which is this one. So this is 3-dimensional simulation in a spherical geometry. And this is the x-axis, so my grid is actually rotating along x. That's a single axis. And I have a B0 pointing in xy. So B0 is actually pointing towards u. And I have a blast wave. And you can see that density magnetic components go out nicely through the pole. And in 3D simulation, sometimes magnetic field, current field loops can be generated out there. So we do put in some diffusive electric field to take care of that, but that's detail, and sometimes it's problem dependent. But generally, it works very well with this kind of problems. And another interesting thing is that one of Joho's graduate students did this experiment in TiGCM. You put in the piecewise linear version of the ring average in TiGCM and get it running in high resolution. So it's a positive, promising sign that the ring average technique can be applied to different models, even like complicated models like TiGCM. I didn't expect it to work, but it works. So, and this is very nice work. So coming back to what's going on in a summary. So what I think is that LFM is a piece of art. So if you talk to people, sometimes CFD people will tell you that computational fluid dynamics is not science, it's not math, it's art. And I kind of agree with that. Starting with, and when you're doing this, you kind of enjoy the fun, in there and getting nice results, getting improvements. And GAMERA is going to be the next generation of LFM. It's under development, and we still have lots of development to do. And the GAMERA is basically based on the high-quality numerics of the LFM. So it's not exactly the same, but we're still improving the numerics at these days, which is good. Starting from 30 years ago, it's still moving forward, which is very nice. And then GAMERA, once the GAMERA can be applied to various problems, and the APL people have already got a SolarWind version of GAMERA running, and we've got some test magnetosphere running on laptops. So if everything goes smoothly, we might be able to run CMIT or CMIT RCM type of thing on our laptops. And I think that would be a very interesting tool to play with. And also, of course, there's lots of details to implement to go back from GAMERA to LFM, because the devils are always in details. So once you get down to the details, you know how difficult it is. So I think there's a long way to go from GAMERA to what LFM's already got. And this is about all we have. And maybe we should do that. Thank you.
Questions?
I just wonder whether your averaging technique prevents you from smoothing.
Mm-hmm.
Equivalent of expansion of your equation set around the singularity and then cutting off at a certain.
It's actually not. So cutting off those things are you're talking about something like filtering, right? You're taking out of the high mode, right? So that process is linear. So the ppm process is nonlinear. So before the ring average, after ring average, I don't lose anything. So my mass, momentum, and energy is conserved after the smoothing. While the other one, you cut off the high K mode terms, you're taking out stuff. So which is something we don't want because we deal lots with shocks. So we want an energy to be conserved. Yes. Yeah, it's just the time step relaxed. So I'm using a large time step to update this chunk. So it's a finite volume. If it's a finite volume, so you update the individual cells and add them together equals to the one because the interface ones always cancel out. Finite difference, I don't know. That's why I'm surprised that it works with TiDCM. I guess maybe the TiDCM solution is so smooth. So, the assumption is always valid. So you don't have to change your finite volume solver. Yeah.
So I noticed one feature not listed is adaptive grid.
Oh, yes, that's an idea that John actually mentioned, that we could do the adaptive grid. But right now, because we're doing with magnetospheres, like even planetary, so you know where the shock is. So you adapt to your grid. Adapted grid is probably good enough and easier to start with. So we do have the possibility, we have the code to generate the LFM grid, if I can make it work. So we can update the grid every hour or something, but that's not our first priority to do. Because Michigan's already do that, so we don't want to do that.